Imagine for a moment that every single thing you owned was slowly but surely trying to disappear back into the earth. It sounds like the premise of a haunting science fiction story or a strange dream, but for almost the entire history of human civilization, this was the literal and frustrating reality for anyone who worked with metal. If you bought a knife, a specialized tool, or a heavy plow to till the soil, you were essentially entering into a long, exhausting, and ultimately losing battle against the very air around you. You could spend hours oiling your tools to keep the moisture away. You could scrub them until your hands were raw, and you could store them in the driest boxes you could build. But the moment you turned your back, the humidity in the air would find a way in. A tiny, insignificant orange speck would appear on the surface of your prized possession, and from that moment on, the clock was ticking. The metal would inevitably flake away, layer by layer, turning into a brittle, useless, and messy powder that we call rust. This was the rust tax, a constant and heavy drain on the energy, resources, and spirit of our ancestors. It was an invisible tax on progress that demanded constant payment in the form of maintenance and replacement. It meant that great iron ships had to be constantly scraped by hand and repainted to keep the salt water from eating through their holes. It meant that the massive, complex machines of the early Industrial Revolution were always prone to sudden and catastrophic failures because a vital internal bolt or a crucial gear had corroded from the inside out, hidden from view until it was too late. For centuries, we simply accepted this decay as an unchangeable law of nature, a tax that had to be paid if we wanted to use the strength of metal. Iron and steel were the strongest materials we had ever mastered, giving us the power to bridge rivers and build engines, but they were also fundamentally fragile in the face of simple oxygen and water. We had found clever ways to fight it, like plating metals with thin layers of tin or zinc, but these were just temporary bandages on a deeper wound. If the thin coating was scratched even slightly, the rot would set in immediately. The world was looking for a miracle, a metal that was strong enough to build a skyscraper, but stubborn enough to ignore the rain. The problem was rooted deep within the chemistry of the materials themselves, hidden away at the level of atoms and molecules. Steel is a magnificent invention, a clever mix of iron and a tiny bit of carbon that gave humanity the power to build the modern world. However, iron has a desperate, almost romantic chemical attraction to oxygen. When they meet, they bond almost instantly to form iron oxide. In most materials, a layer of oxidation actually serves as a protective skin for the stuff underneath. But iron oxide is a cruel exception to that rule. It expands significantly as it forms, puffing up and cracking away from the surface, which constantly exposes a fresh, vulnerable layer of iron to the air. The cycle repeats over and over until there is nothing left but a pile of dust. To solve this, we did not just need a better paint or a thicker coating. We needed a fundamental change in the recipe of the metal itself, a way to change how the atoms interacted with the world around them. The breakthrough arrived in the early years of the 1910s, and like many of the biggest shifts in human history, it happened while people were looking for something else entirely. In a laboratory filled with the heavy smell of coal smoke and the intense heat of furnaces, researchers were trying to solve a specific problem for the military. They were searching for a better material for gun barrels, something that could withstand the incredible heat and the intense friction of repeated firing without wearing down or warping. They began a long process of mixing iron with various other elements, creating dozens of different experimental alloys and meticulously testing their properties. Most of these experiments were failures that ended up in the trash. One specific batch of steel, mixed with a healthy dose of the element chromium, was tossed onto a scrap heap in the corner of the yard because it did not have the specific hardness and strength the researchers were looking for at the time. A few weeks later, someone noticed something truly strange about that discarded scrap heap. It had been raining frequently, and the yard was damp and muddy. All the other pieces of discarded metal were starting to turn that familiar, ugly, and ruinous shade of orange. but one piece was still shining brilliantly in the gray light. It looked exactly as it had the day it was first cast and cooled. It was a small and quiet moment, a tiny observation in a messy workshop, but it was the crack in the door that changed the course of industry. By adding a significant amount of chromium to the steel, they had accidentally created a metal that could heal itself.
The chemistry behind this phenomenon is almost magical in its elegance. When you add enough chromium to steel, the chromium still reacts with the oxygen in the air, just like iron does. But instead of forming a flaky, bulky rust that falls off, the chromium forms an incredibly thin, transparent layer of chromium oxide. This layer is only a few atoms thick, so thin that light passes right through it, making the metal look shiny and bare to the human eye. But that layer is also incredibly tough and remarkably stable. It acts like a microscopic suit of armor that never sleeps. If you scratch the surface of this new steel, the chromium underneath is instantly exposed to the air, reacts with the oxygen, and reforms the shield in a fraction of a second. It is a self-healing material that stops corrosion before it can even begin to take hold. Scaling this discovery from a laboratory curiosity to a global industry was the next great challenge for the engineers of the era. In the beginning, this new stainless steel was incredibly expensive and difficult to work with compared to traditional iron. It was hard to weld and even harder to shape into complex forms. But the potential for a rust-free world was too great to ignore. The first place it really took hold was in the intimate world of cutlery. Before this, even the wealthiest families had to deal with their expensive silver tarnishing or their common steel knives tasting like iron and turning black if they touched an acidic fruit like a lemon. Suddenly, there was a metal that stayed bright, clean, and tasteless no matter what you cut with it. It was marketed to the public as the steel that does not stain, which is where we get the name we use today. As the 1920s and 1930s rolled around, the production methods finally caught up with the ambition of the designers and architects. We found better ways to control the carbon content and the temperature of the massive furnaces, which brought the cost down significantly. This is when the scaling trick really started to change the world in visible ways. It moved out of the kitchen and into the factory on a massive scale. One of the biggest winners in this transition was the food and beverage industry. Before the arrival of stainless steel, processing milk or canning vegetables was a constant and dangerous battle against contamination. Copper and iron vats would react with the food, changing the flavor and creating tiny pits and cracks where bacteria could hide and thrive. Stainless steel was a total game changer for hygiene. It was smooth, non-reactive, and could be cleaned with harsh chemicals and boiling water without falling apart or degrading. It essentially created the foundation for the modern, sterile food supply chain we rely on today. The ripple effects of this material continued into the world of medicine, where the stakes were even higher. Imagine a surgeon in the past trying to perform an operation with tools that could rust or develop microscopic pits, creating tiny crevices where germs could survive even after a thorough cleaning. The introduction of stainless steel for surgical instruments meant that tools could be sterilized over and over again in high-pressure steam without losing their sharp edge or their essential cleanliness. It made complex surgeries significantly safer and paved the way for modern medical implants like artificial hips and heart valves that can sit inside the moisture of the human body for decades without ever corroding or causing a reaction. By the middle of the 20th century, stainless steel had become an aesthetic as much as a utility. It defined the look of what people thought the future would be. The gleaming diners of the 1950s, the bright and polished trim on cars, and the soaring, sun-catching peaks of Art Deco skyscrapers all owed their existence and their permanence to this alloy. It represented a world that was clean, fast, and permanent. We stopped seeing rust as an inevitable and natural part of life and started seeing it as a sign of neglect or poor quality. This shift in perspective changed how we built everything from bridges to washing machines. We began to value durability and longevity in a way that was previously impossible when we were just waiting for the air to eat our creations.
Today, we are surrounded by this material so completely that we hardly even notice it. It is in the pocket of your jeans, as part of the internal components of your phone. It is in the walls of the jet engines that carry us across oceans. And it is in the massive, gleaming tanks that store the fuel for our rockets. We have developed hundreds of different types of stainless steel over the last century, each one tweaked and refined for a specific and demanding job. Some are designed specifically to survive the constant salt spray of the ocean, while others are built to withstand the extreme heat and pressure of a chemical reactor. Despite all these variations, the core trick remains exactly the same as it was on that rainy day in the scrap heap, using a tiny, invisible layer of atoms to hold back the relentless forces of nature.
The story of stainless steel is more than just a story about a better metal or a more efficient factory. It is a story about how a single technical insight can remove a bottleneck that has existed for thousands of years. Once we finally figured out how to stop the world from dissolving around us, we could spend our energy building things that were meant to last. It allowed us to scale our civilization, our food systems, and our healthcare to a level that the researchers in that 1913 lab could never have imagined in their wildest dreams. We often think of progress as a series of flashy and loud inventions, but sometimes the biggest leaps come from the quiet things that simply refuse to change, remaining shiny, strong, and defiant, while everything else fades away into the earth.
We have reached the point where our materials can finally survive the elements for generations. But now we face a new problem: managing the sheer volume of things and people moving through our increasingly crowded world. Next in the timeline, we move to 1914 to see how traffic engineering and the invention of the stoplight changed the stakes for our growing cities. Subscribe to follow along as we explore the next breakthrough in this series.